Hello everyone, welcome to this session. In this session, I will explain a definite integration solving method called trapezoidal method. So let's start. The trapezoidal method is a fundamental method in numerical integration used in approximation the value of a definite integral. Please note that the integral should be definite. That means its initial point and final point should be definite value. The value of a definite integral of the form, say, integration a to b f of x dx. It estimates the area under the curve y is equals to f of x by dividing the interval a comma b into smaller subintervals and approximating the region under the curve as a series of trapezoid. Unlike the rectangle method, which sums the area of a rectangles, the trapezoidal rule uses trapezoids, providing a more accurate approximation. The trapezoidal rule is widely used for its simplicity and effectiveness in many applications of numerical analysis. Here it says that trapezoidal rule is a definite integral solving method. In this method, we will divide the area under the curve into small pieces of trapezoids, and then we sum all the area of the trapezoids, and then we get the value of the integral, that means area under the curve. For example, find the area encloses by the function f of x between x equal to 0 to x equals to 4 with 4 intervals where f of x is given is equals to 4x. Okay. Here I have written the trapezoidal rule formula. So let's start. The trapezoidal rule formula is the formula that is used to find the area under the curve. Now to find the area under the curve using the trapezoidal rule. So let y is equals to f of x be a continuous curve defined on the closed interval, say a comma b. Please note that the function should be continuous in the interval a comma b. Now we divide the closed interval a comma b into n equal subintervals, with each having the width of h is equal to delta x is equal to b minus a divided by n, such that a is equal to x naught less than x1 less than x2 less than xn is equal to b. Now, using the trapezoidal rule formula, we can find the area under the curve as integration a to b f of x dx is equal to area under the curve is equals to delta x divided by 2 into y naught plus 2 into bracket y1 plus y2 plus y3 yn minus 1 and plus yn. This is the formula of the trapezoidal rule, where y0, y1, y2 and yn are the values of function at x equal to 1, 2, 3 and n respectively. Here I have plotted y is equal to fx curve from the x domain a to b, and here I have cut the small pieces of the area under the curve into a shape trapezoid. Okay, and this is the formula of the trapezoidal rule. And then how to apply the trapezoidal rule. The trapezoidal rule finds the area under the curve by dividing the area under the curve into various trapezoids and then finding the sum of all the trapezoids. The trapezoidal rule is not the perfect approximation of the value of the definite integral, as it uses the quadratic approximation. We have to find the value of the definite integrals from a to b f of x dx. The value of the definite integral can be calculated using the trapezoidal rule by following the steps below. In step 1 says that mark the value of the subinterval say n and the intervals are a and b. In step 2, find the width of the subinterval say delta x using the formula delta x is equal to b minus a divided by n. And then in step 3, put all the values of the trapezoidal rule formula and find the approximate area of the given curve which represents the definite integral. Here I have written some applications of the trapezoidal rule. First application is numerical integration. The primary application of the trapezoidal rule is in approximating definite integral. It is used when the integration of a function is challenging and a numerical approach is more feasible. The trapezoidal rule is often part of more advanced numerical integration techniques. In application 2, physics and engineering. In physics and engineering, the trapezoidal rule can be applied to calculate quantities such as displacement, velocity, and acceleration. For example, when experimental data is collected at discrete time intervals, the trapezoidal rule can be used to estimate the area under the curve, providing an approximate of the integration. In uh, 3 is the statistics. In statistics, the trapezoidal rule can be used to estimate the area under probability distribution functions or cumulative distribution functions. This is partially useful in cases where the exact form of the distribution is unknown or complex. Okay, I think this is clear to you. Next, I have written some numerical problems based on trapezoidal rule. First, estimate the value of the integration from 0 to 1. Here, f of x is equal to 1 divided by 1 plus x squared. Using numerical integration by trapezoidal method for 40 different step sizes, comment on the result. I will show you this Python code of solving this problem. Okay, here I have written three numerical problems. I think you may solve this problem yourself after I will show you its Python code. Okay, here I am showing its Python code. Okay, let's start. Here I have imported three Python packages. First, import numpy as np, then import matplotlib.pyplot as plt for plotting these functions, and from scipy.integrate import quad for evaluate the integration using the package called quad. Okay, here I have written the initial point x naught is equal to 0 and final point xn is equal to n. Okay, and here I have written the x domain as np.linspace 0 comma 1 comma 100. Here the linspace mean line space and the space is between the x-axis from 0 to 1, and here I have taken the number of points as 100, and I have taken n is equal to int, that is means integer input, and enter the subintervals. Here I have entered the subintervals. Okay, then I have defined the function which is given in the question. Here I am defining that def, which is a keyword, and I am defining the name of the function as f, and x is a variable, so def f of x, which returns the function that is 1 divided by 1 plus x squared. Okay, and here I have defined the trapezoidal rule. Def is also the keyword, and the trapezoidal I have taken as the name of the function as trapezoidal, and here I have written the arguments x naught, x1, comma n. Here age is the h is equal to x naught minus x0 divided by n, and integration is equal to, first I have taken integration is equals to f of x naught, that means the value of the function at a point x is equal to x naught plus f of xn. Here f of xn is the value of the function at a point x is equals to xn. Then for I in range 1 comma n, k is equals to x naught plus I into h, and the integration is equal to integration plus 2 star f of k, where k is equals to x naught plus I cross h, and then plug the value, integration is equal to integration star h divided by 2, and return the value of the integration. In this way I have the value of the integration using trapezoidal rule and put it into a new variable, say result. So result is equals to trapezoidal bracket x naught comma xn comma n, and finally print the value of the integration using trapezoidal rule is result. You can find the value of the integration using scipy dot integrate dot quad package also in a single line. Okay, you using it you may verify whether the result of your trapezoidal rule is correct or not. So here I have print the value of the integration using scipy.integrate.quad package. Here quad package is, first argument is the function, second argument is the initial point, and third argument is the final point. Okay, here I have plotted this function also, plt dot plot x comma f of x, and I have plotted this function. Please note that enter the sub intervals I have taken as 50. Okay, and the value of the integration using trapezoidal rule is approximately 0.785, and the value of the integration using scipy.quad package is also 0.785. In this way you can verify that your result is correct or not, and the function is look like this from 0 to 1 x domain. Okay, I think this is clear to you. Okay, in this way you can also solve the numerical problems. Okay, you can also solve the numerical problems. Thank you for watching this video.